Let's go, Peter. Okay, it's recording now, so I can share. Check, and we go. Okay. Okay, so we're going to start with the presentation because Michel has to leave early, so he asked me to do it first. Okay, so hopefully, if I have time this year, I'm going to try to do a few like this, like trying to pick a subject and talk about it for half an hour or less if I can. And so today I wanted to talk about Similarity Renormalization group, which is a type of many-body technique that is developed in quantum chemistry at the moment and comes from physics and also nuclear physics. Okay, so as most of the methods, it's been imported in quantum chemistry. Okay, so like lots of different methods, so the Similarity Renormalization group, so SRG, so basically is based on effective Hamiltonian theory, okay, which is a very, very general technique. So what's the idea behind this is you have your, what we call your bare Hamiltonian, so your starting Hamiltonian if you want, and you're going to modify, to transform it thanks to a wave operator, omega, like this. And you're going to transform that bare Hamiltonian to get an effective Hamiltonian, which usually it's easier to handle. Okay, so if this one is complicated, sometimes you want this effective Hamiltonian to be less complicated if you want. So that's the idea behind this. So that's what we do in Loveden's partitioning techniques, for example, where we do a downfolding of the information. Okay, so I think I've talked about the Loveden partitioning techniques, where you're going to downfold some information onto a smaller space. Okay, and by doing this, you're going to create an effective Hamiltonian, which is usually smaller, but can be also sometimes more tricky to solve. Okay, so there is lots of methods that use this effective Hamiltonian theory. There is the transcorrelating methods. There is multi-reference perturbation theory, multi-reference couplet cluster, or single reference couplet cluster for ground state. Fock space couplet cluster as well does that, and equation of motion couplet cluster, which is also based on effective Hamiltonians. Okay, so it's something that is used a lot. I don't think, maybe even like techniques like quantum Monte Carlo, we can say that it's they use effective Hamiltonian sometimes. So something very, very general. So before like talking about the SRG technique, I wanted to just define things properly in terms of mathematics, just to give you what is the properties of this similarity transform that we do. So here it's a similarity transform of the Hamiltonian. So we say in mathematics, so if we have two n by n matrices A and B, we call them similar if there exists a matrix S, which is also n by n, such that S minus 1 AS is equal to B. Okay. And so the main property behind that that transformation is that it does conserve the spectrum of eigenvalues of A. So if lambda is an eigenvalue of A for an eigenvector X, actually lambda is also an eigenvalue of B with different eigenvectors, okay, S minus 1x, okay. So really you can see the idea here in quantum chemistry is that you have a matrix and you want to know its eigenvalues because that's the energies, okay? And so this matrix is complicated or big, so that what you want is to modify it through a similarity transform to make it simpler. And by doing this, you're not going to change the eigenvalues, but you're going to change the eigenvectors, okay? So that's really the main purpose of similarity transformation is to reduce the complexity of evaluating these eigenvalues. So we know lots actually of similarity transformation. So you know that, for example, if A is diagonalizable, okay, so you know that it is similar to a diagonal matrix because you have this transformation that goes through from the original matrix to the diagonal matrix, and that transformation, if it is diagonalizable, it's a similarity transform. Okay. And what is nice as well is that even if A is not diagonalizable, actually it's not similar to a diagonal matrix, otherwise it could be diagonalizable, but it's similar to a matrix in Jordan form. So for people who don't remember what is a Jordan form, it's an almost diagonal matrix like this, but you still have ones in those blocks, okay? And on that upper triangular matrix, by the way. Okay, so you can approach a diagonal matrix, but not quite, okay? But it's much easier to diagonalize than the original matrix. So if you have a unitary transformation, for example, a special type of similarity transformation in which so the inverse of the similarity transform is actually equal to the SDAG. Okay, so transpose complex conjugate. Okay. Okay, so and that shows you that every Hermitian matrix, okay, is unitarily similar to a diagonal real matrix because you can always diagonalize an Hermitian matrix, and you know that the eigenvalues are actually real because it's Hermitian. Okay, so that's the mathematics behind it. So when we talk about effective Hamiltonian theory, we always talk about the what we call the model space, which is the main space, the space that you really want to do things in it. Okay, and you have also the external space, and you basically split your space with model space and external space. Okay, so for example, you have what we call a reference wave function psi 0, which basically is going to define your model space. Okay, so it can be defined as a sum of determinants, but it can be something else. Okay, it can be only one determinant if you want. Okay, and so we define the projector onto that space P, and you have like the complementary space, what we call external space, which is 1 minus P basically. Okay, so so sometimes you don't have to build that space explicitly because it's actually given as the complementary of the other one. So, so the problem is that we have lots of different terms for model space. Sometimes we find like reference space, zeroth order space. Sometimes external is called perturbers or first order space and so on. But basically, the most common terms are model. So that's the main little one, P here. And you have the external space, which is the big one that you want to fold onto the small one. Okay. So that's basically the purpose of the law of Dean partitioning technique, where you actually write the original Schrödinger equations as blocks, and those blocks actually are going to be in different space. Okay, so you have PHP blocks, which is here. Okay, those coupling blocks over there, and the blocks that correspond to the external space. So what you're trying to do usually is to fold information from those blocks into that block, okay? Because you want to have more physics in it. So that's what we call dressing, habillage en français, okay? And so basically that's the purpose of all the techniques. So for example, in traditional couplet cluster, what you do thanks to this exponential t actually is to put that block to 0. Okay, so you're going to rotate everything to put that block to 0. Okay, and so you end up with the effective couplet cluster Hamiltonian, which is non-Hermitian because it's not diagonal, it's not symmetric anymore, or Hermitian. Okay, if you do unitary couplet cluster, when here you do a unitary transformation, So you keep the Hermitian, your Hermitian effective Hamiltonian. But what your purpose in unitary complex cluster is to put this block to 0, but also this block. Okay. So that's two types of effective Hamiltonian theory. So if you've read a little bit about multi-reference complex cluster, for example, or multi-reference CI on all those methods, you always talk about. They always talk about intruder states, and because the intruder states are going to give you convergence issues. So why is that? Is because if you're doing perturbation theory or complex cluster, basically it happens that if you have, for example, badly chosen your model space, so you haven't put all the determinants that you wanted, or for example, it's too small, you cannot put more determinants because it's going to get too big and so on. It happens sometimes that determinant from the Q space actually becomes near degenerate with a determinant in the P space. Okay, and so if you do that, you have the appearance of small denominators. So because you have lots of terms which are one of the difference in energy. And because you have this, you're going to have like convergent issue, because you're going to have 1 over a small number, and you're going to get like lots of troubles. Okay. And so basically the idea here is to how to avoid intruder states is to make sure that you do not enforce QHFP equals 0. So what you want to avoid to put those blocks to 0, because if they really are, if they are near degenerate, you don't really want to decouple them. Okay. And so how do you do that? You want to avoid that near degenerate determinants are decoupled. Okay. And so that's exactly the purpose of the SRG transformation, which actually is going to transform your original matrix to something which is basically band diagonals. So they're not like big zeros there, they're going to be small numbers, but it is going to choose the determinants to decouple from the model space, but it's going to choose them by looking at the determinants. So if the determinants are too small, it's not going to decouple them. You're going to keep the coupling so that you don't have those convergence issues. Okay, so for example, on that figure, so if you say that the white part is zeros, so you're going to decouple the determinant that have a large denominator, because you know that in that case, there is no problem. You can decouple them. You're not going to have issues. But if you look at the determinants that are in the gray area there, they're going to be determinants that have small denominators. So you want to keep them coupled. Okay. So that's the idea behind this transformation. So is that clear for everyone so far? If you have a question, do not hesitate. No? We're good? Okay, so so just an historical overview of the SRG that some people call a flow equation. So you might see like the two terminology. So the SRG is a continuous transformation, okay, that's going to depend to a parameters I'm going to show you after. Okay, and it's been introduced by Glazek and Wilson. So Wilson is the Kenneth Wilson Nobel Prize. So it's something that goes from quantum field theory. And so the main idea, that's exactly what I told you, is that SRG decouples the Hamiltonian starting from states that have the largest energy separation, and you progress toward the state that have smaller energy separation. So basically, when you're going to go to full SRG, okay, so the parameters is infinite, you're going to strictly decouple the P and Q space, okay? So it doesn't enforce this constraint to make sure you don't have intruder states problems, okay? And that's a theory that actually has been designed in quantum field theory, but it's also used a lot in nuclear physics. Okay, so as a single reference method, but also as a multi-reference method. Okay, and why is that? Is because they have all the technology to deal with 3 or 4 body terms in nuclear physics, so they use that a lot. Okay. So there is the first paper that appears in chemistry based on the SRG is by Stephen White. So Stephen White is the researcher that basically invented DMRG, for the people who know what DMRG is. So you see that there is 2 letters in common between DMRG and SRG. So it's probably a reason for this. And so in chemistry, since I think 2014 was the first paper, it's been developed in chemistry by the group of Evangelista in Atlanta. Okay, and here is a review, by the way. And here is the first paper that he did actually, which is quite nice actually. Okay, so what is the idea behind SRG? Okay, so you're going to do a continuous transformation of your Hamiltonian. So that's your bare Hamiltonian that you transform into a S-dependent Hamiltonian here, H of S, by a unitary transformation. Okay, so here it's not a similarity transformation; it's a unitary transformation. And what you're going to be able to do is you're going to be able to choose that S parameters actually. Okay, so basically, if S is 0, okay, you're going something that is basically the original problem. So you're not going to decouple anything. And as S gets bigger and bigger, you're going to decouple more and more until you reach the limit where the P and Q space are completely decoupled. Okay, so you have hard zeros in the off-diagonal blocks. Okay, so so in the following, we're going to write everything in terms of many body expansion. So I define like the Hamiltonian in terms of 1 body and 2 body terms. Okay, so those notation A, PQRS are this. That's the annihilation and creation string of operators. Okay, so I'm going to use those short notations. So basically, so if you increase S, that's what I was telling you, H is becoming more and more block diagonal or diagonal if you are in a single reference space. Okay, and so the S variable is called the flow variable. It controls the extent of this transformation. Okay, so it's like a button that you're going to be able to turn. And the more you turn that button, the more you decouple the 2 spaces. Okay, so that's what I was telling you. S equals 0, the transformation is unitary. Okay, it's just an identity, sorry. And so you have the original. And when S goes to 0, you really decouple. So what I'm going to use in the following a lot is basically show that we write H as a sum of the diagonal part and its off-diagonal part. So here I'm going to use D and OD. And so in the limit when S goes to 0, so actually that's going to be our main conditions. Okay, so that's the conditions that we're going to use a lot, is that we know that in the limit it has to be equal to 0. Okay, so that's basically S equals 0 and S equal infinity. That's the 2 boundary conditions that we're going to use in other terms. So if you differentiate these equations with respect to S, the flow parameters, you're going to end up with an ordinary differential equations that is given by this, and you have your boundary conditions. Okay, so here you have the derivative of H with respect to S is going to be equal to that's a commutator. Okay, and you have this H of 0 equal H. So the idea of SRG is to actually integrate numerically these equations. Okay, so the thing is that you don't know eta, because eta is a complicated thing that is basically so it's called the flow generator or a flow operator sometimes. It's an anti-Hermitian operator, but you don't know it because it depends on your unitary transformation, but you can parameterize it. So and that's that's the key here, is that you don't know it, but you can find a form that is you think is suitable for your problem. Okay. So the take-home message that what I wrote in the little box is that you can find suitable parameterization of eta to allow integration, numerical integration of this guy, okay, in practice. And so you're going to be able to find a numerical solution of H of S that satisfies the boundary condition without having to explicitly construct the transformation U of S. Okay, so that's the idea. So we enter the world of DFT, where we have to guess stuff, construct stuff. So there is a few generators that have been proposed, obviously, in the literature. So there is a Wegener's canonical generator, which is defined basically as the commutator between the diagonal and the off-diagonal parts of the Hamiltonian. Okay, and actually you can show that as long as this generator is not zero, actually the derivative of the trace of this operator is going to decrease. So basically, as S goes to infinity, you're going to decompose more and more. And so what you're going to show is that your expectation value of the Hamiltonian H of S for your reference wave function is going to evolve, okay, towards an eigenvalue of H, okay, because it's a similarity transform, so same spectrum. And one of the eigenvectors is going to evolve towards something that looks like an eigenvector of H, but you have this transformation U of psi 0. Okay, it's not, it's a similarity transform, so it's same eigenvalues, but it's different eigenvectors. Okay. So the problem is that in practice you cannot do that when you have n-body terms, because basically this transformation actually, so your starting Hamiltonian has 2-body terms at least, at best, or at worst, let's say. So if you look at the Hamiltonian, you have the 1-body and the 2-body terms in quantum chemistry. But by doing this transformation, there is no free lunch. So basically, you're going to make things simpler, but basically, you're going to increase the complexity of your Hamiltonian. Okay. So basically, when S is going to grow, you're going to add some 1-body terms, some 2-body terms, some 3-body terms, up to basically the number of electrons. Okay. So because when you basically compact information, you really have to put the information somewhere. So don't think it's vanishing in the air. It has to go somewhere. But what you can do is you can choose to truncate your Hamiltonian to, for example, 2-body or 3-body or 4-body, and say, I'm going to stop like this. And so in practice, if you increase the maximum order of your terms, you should converge to the exact solution. So for example, if you truncate to the n-body terms, you're going to have a method which is called SRGn. Okay. So basically the simplest one, non-trivial, is going to be SRG2. So it's basically like doing couplet clusters, singles and doubles, where you stop at the 2-body terms. Okay. So what is interesting to do is to do a perturbative analysis of the SRG theory. So what you can do, you can expand all the energies and the Hamiltonians as a function of parameters, as usual, that correspond to scaling the 2 electron terms and so on. And so you can do this. So you expand everything in terms of lambda, like you do in Moeller-Plesset perturbation theory, for example. And actually, if you do this and you look at the first order amplitudes, first order of diagonal components of the Hamiltonian, so what you can show, so you can find the expression analytically, actually, if you use the Wegener's canonical generator, and you find something like this. So that's this expression here, sorry. Okay, and so basically, so that's nice. And so if you're looking at them, you can see that when the denominator is large with respect to lambda, so S is homogeneous to 1 over energy square. So if you want a parameter that is scales like an energy, you take the inverse of the square root of S, gives you something which is homogeneous to an energy. and you can look at how the different quantities scale corresponding to this value. And so if you have denominators that are very large with respect to S, you can see that those amplitudes, those first order of diagonal components of the Hamiltonian, they basically roughly equal to 0. So that's what I told you before, is that if you have a large denominator between two determinants, you are safe and you can decouple them. Okay, so that's exactly what you want. But basically, if the denominator is smaller with respect in comparison to that energy cutoff, basically it's going to say, no, I don't decouple them and I leave it like they are, like just like a double bar integrals, like in MP2 basically. Okay. And so what is interesting is that you can look at the expression of the second order energy. Okay. And again, in the case of this Wegener's canonical generator, you can do everything analytically, and you end up with that expression. Okay, and if you know the MP2 expression, you can see that this expression is actually very, very similar to the MP2 expression, but you have here what we call a renormalization factor, and actually, for people who know those things, that's basically the terms that you use in theory that renormalize the MP2 energy. Okay, if you, when you have like near degeneracy in a system and you use MP2, everything blows up. But you can try to regularize the MP2 energy or to renormalize, and that's basically the stuff that you're going to use. And so you can check that for any value of S, even if delta is small, that thing is never going to blow up. Okay, and actually we had a look at stuff like that with Mika when he was doing his master degree to regularize, for example, the expression in GW, where we have the same problems. So it's something that is very well known. Is used in methods like kappa MP2 in QChem, for example. They use this. Okay. Okay, so the main drawbacks of the SRG method is that you have to solve those differential equations, okay, and we know that it's usually more challenging and less numerically robust than solving a good old set of polynomial equations where we have to find zeros, okay. And so, for example, we also lack the exponential form that we have in couplet cluster theory that makes everything like size consistent and so on. And so that's why Evangelista proposed the driven SRG, so that I'm going to call DSRG, which basically tries to solve those two problems, okay? So here, instead of having this operator U, is going to exponentiate the transformation, okay? So here, you use exponential of A, okay? And that's a unitary transformation. Okay, why is it a unitary transformation? Because basically A is an anti-Hermitian operator. And now you know that if you take the exponential of an anti-Hermitian operator, you end up with a unitary transformation, always. Okay, so you have something that depends on S, and that's basically exactly the ansatz that you're using in unitary couplet cluster, actually. Okay, so that guy is very, very similar to unitary couplet cluster, but you have this S dependence in the transformation. Okay. So you can expand again, as usual, T, that's the amplitude that you want to find. That's just exactly like in couplet cluster. So you have a couplet cluster form, okay? So we expand in terms with cluster amplitudes this operator. So we're going to have the singles, the doubles, the triples, and so on, okay? And so what you can do is basically say what I want is I want to decouple, I want to make the off-diagonal term of that Hamiltonian to 0. So what you're going to do, you're going to say, I'm going to define that as a source term, okay, the source operator. And basically, the source operator is going to drive the off-diagonal component of H to 0, okay. So here you see that I'm using a bar, okay. So before I was using a hat, and now I'm using a bar to make sure we are in the DSRG level. And by the way, here, it should be a bar, okay? And so basically, as we know this, we know that the condition that we need to make sure that our calculation is converged is that this minus this must be equal to a residual, which should be equal to 0 at convergence, okay? So that's the same idea as in couplet cluster. Okay, you want to find a set of equations to set to 0, so that you're going to find the different components as zeros of polynomials. Okay. Okay, so again, many body expansion of those residuals, and you end up, so the little omegas are the first body, the 1 body, 2 body, 3 body components of that operator. And basically what you're going to have to solve, you're going to have to solve those omega ij ab of s equals 0. Okay, all those, that's a set of polynomial equations, and the roots of those equations are going to give you the t's. Okay, basically, and that's what you're looking for. When you have the t's, you have everything to compute the energy. Okay, and so again, the usual trick, you can truncate the t's to a given order n. So you say I'm stopping at n body terms, and so it's going to be DSRG n, sorry. And if you truncate to 2 bodies, it's going to be DSRG2. Okay, it's basically like CCSD. Okay.
Two stupid question. Yeah. Here the S is a fixed parameter when you do the calculation?
Yes, it's the fixed parameter. So you have to do 1 calculation per value of S.
Okay.
So that's something that I don't really like about the method, because a priori you don't really know what value of S to use. But that's what they do. Okay. All right. So so now what we can do is we can expand the source term, the source operator, many body expansion, 1 body, 2 body, 3 body, and so on. We can do the same for the medi body for the H bar Hamiltonian. Okay. So here it doesn't stop at 2 body. Okay, it goes to 3 body, 4 body, 4 body, and so on, because it's a S-dependent operator that is a transform operator. So there is much more than 2 body terms. And basically, because I know that I need to solve the omega equals 0, and because omega are basically the Hamiltonian transform minus the source operator, basically the DSRG equations are basically, I want to solve equation that looks like this. So my H bar component, IJAB of diagonal, okay, must be equal to that source term. Okay. So you see here that if you want to solve those equations, you need two things. You need to be able to compute those H bar, and you need to be able to compute those source terms that you actually don't know a priori. Okay. So for the first one, for the Hamiltonian components, okay. So if you had the bare Hamiltonian, you would stop at 2 body terms. So it will be straightforward. But here it's a many body operator. Okay. And the worst is that because you do a unitary transformation that looks like T minus T dag, actually you can always write that expression as a Baker-Campbell-Hausdorff formula, okay, which is a sum of nested commutator. And if you do couplet cluster, by the way, this series is going to truncate to the 4th term. You know that, because the Hamiltonian is a 2 body terms. But in the case of unitary transformation, it actually does not terminate. Okay, so it's even worse than a variational couplet cluster calculation. At the variational couplet cluster level, it does truncate at the number of electrons. But in the case of a unitary transformation, it doesn't even truncate at the number of electrons. It never truncates. Actually, it never terminates. Okay, and so why is that? Is because here you can see that you have excitations, and here minus de-excitations. So you keep exciting and de-exciting at the same time. So this thing never terminates. Okay. So you have to find a way to truncate somehow these commutators. Okay. And so in DSRG, they use the Yanai-Chan linear truncation scheme, okay, that is like this. Or basically, you linearize each commutator, and you say that basically, if you want the commutator up to, so this curly bracket here is up to m body terms, basically, you're going to compute them as the sum, because it's linearized, of all the commutator up to a k body exponent. And you sum from k equals 0 to n. Okay, so that's an approximation. because in theory it goes to infinity. Okay? And so now I gave you a recipe to calculate the H bar matrix elements, but you need also the source operator elements. Okay, and those ones a priori you don't know them. But what is nice in that method is that you can parameterize those terms. It's like this eta parameter that we had, this eta operator that we had in SRG. Now we have the source operator in DSRG that we can parameterize. And so Evangelista proposed to use that form, okay, here, which is basically based on the perturbative analysis. So basically this form, you can see that it's roughly the form that we had for the SRG methods. Okay, so you guess a form for this, and you say that your equations are going to be solved when the H bar, the off diagonal H bar elements are going to be equal to those off diagonal source term elements. Okay. And so what is important in those source term parameters is that they have to fulfill the boundary condition of the problem. So here you can check that if S equals 0, you recover the bare Hamiltonian. And if S goes to infinity, well, you decouple exactly your reference space and the excited determinants. Okay. So here I'm talking about the single reference DSRG. Okay. Any questions so far? No. So now let's do DSRG2. So that's going to be the equivalent of CCSD for DSRG. So I truncate T to T2. Okay, so it's T1 plus T2. And basically, so we have two sets of equations. We have the singles, okay, so H bar IA equal R IA, and the doubles, okay, H bar IJAB is equal to R IJAB, okay. So the source operator, I know them. It's just the same formula for the two components that I just gave you before, okay. And I can use the tricks by Garnet-Chan and Yanai to compute that commutator that does a BCH expansion that never stop. Okay, so there is a recursive formula to do this that you can apply. And basically what you can show, that what is important here is that you can show that this computation of the commutator is actually the computational bottleneck, and it's actually O square, V square, N square, which is basically it's slightly more expensive than complex cluster singles and doubles, but only slightly. So CCSD, it's O square V4, okay, and so here it's O square V square N square, okay, where O and V are the number of occupied and Gertrude. So it's a little bit more expensive, but it's marginal, okay. And so basically what I can do is I have an updating scheme like in couplet cluster. So I start with a set of amplitudes that are given by perturbation theory. So 0 for the singles, and here that's the amplitudes that you get from second order perturbation theory. And I update them. So basically I have my starting amplitude. I can plug them here and there, okay. Delta is given, okay, from the artifact calculation. And S, I know them, it's an input of the program. And the H bar elements, I can compute them with the Yanai-Chan tricks. So I can get some new T's that I can plug again, can compute a new H bar, and so on, until convergence. Okay?
T2?
Yeah.
T2 question. So at the bottom here, the TIG-JAB, it's the same equation as the renormalized MP2?
Yeah, exactly.
So in fact, it's you take a CCSD, instead of doing MP2 as a guess and iterating over it, you do renormalized MP2 and you renormalize when you...
But you have to be careful because the updating schemes is different from CCSD.
Because it's not, it doesn't truncate.
That's right. Because
okay.
Mostly because of that term that doesn't truncate.
Okay.
So yeah, and that's the most expensive to calculate actually. So you can see it as a basically, those guys here are the equivalent of the residual to compute in couplet cluster. Okay, but they're less easy to compute because they never truncate. But the rest is the usual stuff. So basically, if you have a couplet cluster term and you know how to evaluate those H bar elements, you're done, pretty much done.
So if you do S goes to infinity, you do CCSD?
No, you do unitary CCSD.
Okay.
Because the ansatz that you use is not a traditional couplet cluster ansatz, it's a unitary couplet cluster ansatz.
Okay.
But so I think in the first paper, Evangelista had a look at the traditional couplet cluster ansatz, but he said that it doesn't work very well. So I don't know.
Okay.
So I haven't done anything myself. I mean, I'm just reporting what's in the paper, or what I've understood in the paper. But,
yes.
So I don't know much more than this. Okay.
Okay.
And further readings if you want to read more about this. And I think that's it. Going to